I'll just keep going. So we have seen now so far 1D, 2D systems. We're going to now see a way to do a pseudo 3D system. I call it pseudo 3D because it's not really that we're going to look now in this system a true 3D system of CA, but we're going to see how to represent in 3 dimensions 2D systems. So we're going to start with that because that's going to help us to later make the actual 3D system. So basically, we don't need to really implement anything here except for a visualizer, because we already have this, which is the 2D system that we already implemented. So game of life, Brian's brain, and MNCA. We can use all of those to make these stacks. That I call them 2D stacks. So the principle of these stacks is this. And one of the hardest things of this workshop was to make these things look like that. But okay, I managed. And what we're gonna do is basically stack the 2D versions in time, one after the other, in 3D textures. So this is what we're gonna implement, basically. And we're gonna make a visualizer to read them and represent them with cubes. So that's what we're gonna do. Okay. Basically this, like I said, nothing, we can use a game of life, for example. And what I'm doing here is I'm passing it to some visualizer so that we can do this. So if we see, for example, the game of life, if I do a visualization with the system, then it creates a stack like this. And you can see how it grows. And every time will be slightly different, I think, or I didn't do that. And it's not changing because the noise condition of that system is not updated. I thought I did that, but you can change it and it will be different. Maybe if I change the probability, of course, that will have an impact. So as you can see, then we have different results. So that can be cool. Looks like coral or something like that. And that is nice. You can experiment with this a bit. And you can also try the other ones that we have. So I'm looking at game of life. Let's see what Brian's brain does. It does this kind of stack and MNCAs. And of course, we need to choose an MNCA that actually works. So maybe we choose some 2, maybe 16 again. 16. Okay. So we'll do this, then we can play also with them. And you can see that something happens. Although, yeah, may not be the most interesting ones. So just play a bit, see what you get. But basically, let's just quickly dive to see how that works. I think all of you, I think, are quite familiar with instancing and how that works. And but I'm going to explain just a couple of key elements here, which are the 3D textures, which is I'm using here a texture 3D to stack the frames, and that's what's happening here. And I'll replace that with some operator, nothing very fancy here, just very simple. Stacking that in a 3D. You can do this better so it doesn't lose any frames. And I have done that later, but just this is a simple demonstration. You can also do this not real time, so you don't lose any frame. And then you have all of them. And that 3D texture is passed here. My 3D texture, as you see here, is 80 by 80 by 80. So we need to find a way to read this 3D texture into here to make those cubes. So that can be done with a vertex shader, for example. So here a vertex shader to read those. I'm not going to go over this too much detail because I want to go quickly to the 3D system. But just to explain very briefly, here we have a converter from the instance ID to XYZ coordinates. And I am basically just creating a box with those coordinates in 3D space. This is creating that box. And basically finding out the locations for each one of those instances, which are in reality just these boxes, nothing special, just a box. And those instances get moved in space and placed according to the locations of that grid. And after I am applying to the color, just a mix between these two colors using the depth value. And the depth value is, you can access it by doing this, using the index to XYZ function I provide. So this calculates also the Z, which is the depth of the texture. And yeah, that is pretty much what this is doing. And obviously, I am fetching this data, is fetching from the 3D texture, the state of the cell, and I'm using that state as an alpha channel as well to not draw things that are below certain threshold, in this case 0.5. And in that way, we can render cubes. Okay, so this is relatively straightforward. I hope that is clear. And that principle is what we're going to use now that we'll do a true 3D implementation. So to mark the distinction once more, this that you see here is just stacking 2D. So this is not a true 3D version of our automata, it's just stacking 2D slices. But now we're going to do a true 3D system. So using the third dimension to look at those neighbors. Okay. So let's build here, the basic version. And the principle for doing this is exactly the same as the Totallistic version in 2D, that Brian's brain thing we checked. So I moved over quickly over that so that we can do this. Okay, so let's just begin. To start with, I think we need to find a way to create some to create some random states for the initial state, right? And that means that every voxel, because now we're talking about 3 dimensions in the texture, so every voxel in space needs to have a random value, and that will be the state, a random state. So there's a couple ways we could do it. I thought the easiest way is to just make a 3D texture ourselves. So let's just do a GLSL here. We're going to need to set a couple of things here. So let me see. Here we need to say that it's going to be a 3D texture. We're going to do a custom depth. We're going to do that this matches the dimensions that we have here. So the dimension, I'm going to copy that parameter. Dimensions. And dimension here. So in this case will be 80 by 80 by 80, right? And now we have a 3D texture. Now to write, let's write something inside. We're going to write in here something for our pseudo random number generator, but that's now things in 3D. So I'm going to use this function by David Hoskins. This one, nice hash. So 1, 2, 3. And we're going to do something similar that we did before, but this time we're going to access also the Z, which is the depth in the 3D. So we're going to fetch the resolution. And the resolution is equal to and also, so let's start using the vector and the depth. So to be output info that's y. So the y gives us an integer value, which is what we need. All right, so this will be the coordinates in 3D space. So, but we're going to convert them now. Sorry, not the coordinates, the resolution. And now we need to compute the coordinates. So the coordinates will be this by 3. Then we need the coordinates as we had it. And then we need the current depth. Okay, now this will be the coordinates in pixels or in voxels, I don't know anymore, in 3D space. And now we need to compute some random value. So for R, we get a hash. It takes 3 things in, so XYZ, and gives us 1 random value. And now we're gonna choose that things that are closer to the center are gonna be used, and things that are further not gonna be used. Basically, we're gonna look inside the sphere. So what is inside the sphere, it has a value of 1, and what is out, it has a value of 0. If we do that, maybe you remember from some ray matching things that you may have done. We're gonna do this, and this should give us some length based on the coordinates. So we're just checking, creating the sphere. And finally, we define a state. And the state is going to be if this is different, it's smaller than some radius. So the radius we're going to choose. Then we're going to multiply that by the random number that we have here. If that random number is smaller than some probability, but we have some control over what's the number of things that we're going to get. And maybe let's make also this just a single channel. We don't need all those 4 channels, and the value is going to be state. Okay, and now we need to pass, of course, the uniforms, right? So uniform, the radius, okay, probability, and maybe if we want to have different values over time, we can pass also with time for later on. Now let's here add those radius. Probability. And time. And we're not using it for now, but we'll just pass it by the way. So as you can see here, the center one on this 3D, because it's 3D, of course, we have to imagine it like a grid, that all those pixels are in a grid now, and a cube. Then our radius is gonna be about 80. So 80 is all the box. So if we want to have more or less half of it, then we have to say 40, maybe less. But here you can check how many of those boxes in space have the value 1 that we have here, right? Okay, so that's how we can make some randomness, and we can, with this probability, control a little bit more as well what happens. So if we discard some pixels or not. Okay, I think, yeah, that's good for to start with. So this is going to be the random states over 3D system. And that is perhaps the most different part that we have done. Then the rest is pretty similar. So let's just do constant feedback. GLSL. And we're going to connect this one there and this one and the second input. And then we need to know. Okay. And now let's check the code for the 3D implementation. So in the 2D implementation, everything is pretty much same. So let's just do the same principles. It's pretty much the same. So I like 3. Now we have, remember before we had XY, now we have XYZ. That will be the GL. And then we also have the depth of the shading. And this one, of course, needs to be of the size dimensions. Dimension. Okay, so yeah, and we need to make it a free texture. Okay, and now we have XYZ. Now, next thing, we need to define our cell. And like before, sorry, that's the cell. Then we need to define the properties of cell, which is the position. Then we have states, but now we have more than one, and we can have neighbors as well. That's so we can do something with the colors later on. Okay, so now let's define our cell. The position is going to be that location in 3D. The states are going to start with 0, and the neighbors are going to start with 0 as well. Now we're going to check the state of the cell when it comes in. So the state is going to be equal to, again, an integer. We're going to use vector fetch. And we're going to use now the std 3D inputs from the input. So let's define here input to be 0 and define randomness to be 1. So input, and here we will pass our XYZ. And again, 0 here because it's vector fetch, so we need level of equal 0 to capture everything, and we only need an int. So okay, there we have it. And we can make something. The state is non-member, so here say states. Okay, then we need a way to reset this. So we get reset. I don't know, uniform. The reset is bigger than 0. Then the state is going to be equal to this, but instead of fetching from the input, we're going to fetch from the random part, from the random generator that we just wrote. Okay. Oh, you know what? Let's call this state. States. State. State. Okay. This is just one state, of course. All right. And otherwise, we do the check function. Check neighbors, as we have been doing. Okay. There we go. So now let's define check neighbors, as we have done so far. Now cell C. And our check neighbors function now will look different, of course, because now we have 3 dimensions. So first we need to define our neighborhood. So we're going to define a Moore neighborhood again. And if you remember the Moore neighborhood, we have something that it's just this lattice, this grid that we're looking around. But since we're in 3 dimensions, now we need to define a Moore neighborhood that is a cube, not just a plane. So that will look like this. So that's a cube sampling. Yeah. So we have the first matrix that will be the part behind the current cell, the lattice and the current cell, and the lattice in the front of the cell. That's how you define that in 3D. So there's a cube sampling. And now we also want to use a different neighborhood that is called the von Neumann neighborhood. Von Neumann neighborhood. And the von Neumann neighborhood is named after the originator of Cellular Automata. He used this neighborhood and he did his implementation. It's also called diamond sampling. So instead of looking at everything around it, we just look on the ones that are adjacent, immediately adjacent. So kind of like a plus if you're having 2D, or a plus with an extra side in 3D. So that's what this does, right? It is the same thing. Okay. Now let me see. We're gonna add here into our code a way to read, of course, from these neighborhoods, but we're gonna need 2 because the neighborhoods have different sizes, right? So we're gonna need to define the Moore neighborhood. Or you know what, let's just copy this so it doesn't take much time. I'm just gonna explain it. Okay, so the move neighborhood is gonna call the get move coordinates, which are these, right? So we get all these coordinates, and then I find the resolution just so I can do that I did before, which is to wrap around. Remember, mod is just modular, but for all floats, just to use this, it has to be an integer. And also this doesn't really work with negative numbers. It will not wrap around for negative numbers, it will just give you 0 or -1. So you need to use mod if you wrap around the negative side as well. And we use floats, so that's why we use mod. And then the rest you are pretty familiar with. In this case, 26, we iterate over 26 because the coordinates that we have, of course, are 26. So we need to check all those in space. And we do the same for the von Neumann neighborhood. And here comes something that took me a long time to understand. It really got me stuck because when I implemented this, I was sure I was right, but still not getting the results. Something that is super important when you implement the systems is that, of course, in 3D and in 2D as well, but in 3D is more apparent because of how you have to lay out the rules. You only need to count the alive states. And remember, at the very beginning of the workshop, I told you alive means one and only one. It doesn't mean anything else. So it could be that your neighbors are in different states. Remember, we talked about decay states. So it's at 0 is dead, 1 is alive, and there's other decay states, could be 2, 3, 4. So whatever state they're in, if they are dying and not dead or alive, you don't count that. In this case, you only sum up those that are exactly alive, so exactly 1. This is the crucial point here, very important. When you're going to implement them yourself, that took me a while to figure out. Okay, so that's something. Let's move this cell at the top. That's not going to do it work. And you know what? Let's add also here states for later for drawing something nice. We're going to also keep track of how many states the thing actually has. Okay, and now we need to define our rules. Now, how to define rules in 3D? Remember that I told you that there's this algorithm that we can use, algorithmic way to define the rules that has to do with a survival rule, a death, birth rule, a death rule, and a decay, or let's say dying state. So we saw that when we briefly mentioned Brian's brain, I skipped it so I can explain it here properly. We're going to use this principle as a general way to define every system in 3D. And this is very powerful because it allows us to do something cool, which is a general solution for all cases that I'm going to show you in a second after we do this here. So I'm going to show you, for example, one algorithm that works. For example, rule 445. It looks like this. We have to define the states. In this case, the states of the system are 4. Then you have to define what neighborhood we're going to use. In this case, we use a move neighborhood. And then you basically need to create the birth, survival, and decay rules, which is the birth, the survival, birth, decay, and then the death. But the death is implied because what doesn't satisfy these questions is already death, so we can ignore the death rule. The survival, birth, and decay. And this dying state gets implemented by entering into a state that is not 1, but is something else than 1. In this case, since there are 4 states, the cell can be dead, alive, or say in this case, there are 4 states other than dead. So in reality, there's 5 states, right? 0, 1, 2, 3, 4. But state 0 is dead, state 1 is alive, so there's 3 extra states that we can take. When we have entered into that decay zone, which will be 2, 3, 4, that's what's happening here. We're just adding 1 to the previous state. If the cell is already alive or dying, we're just adding up and wrapping around whenever it reaches the final state, in which case it will die. So when you wrap around C states, it's going to become 0. And if it becomes 0, it only becomes alive again if this is satisfied. So that's how the system works. So one more time, just so it's very clear, very briefly. If it's dead and has 4 neighbors in this rule, of course, this will change per rule, but in this rule, then it becomes alive. If it's alive and it has these neighbors, then it stays alive, survival. And it decays whenever it's alive or in a state other than alive, so dying. And we update that by adding 1 and wrapping around the maximum state it has. So it dies at some point. And then, of course, everything else is dead. Yeah? Okay, so let's try to do our check neighbors with this rule. We're going to use rule 445. It's called rule 445 because there's a notation system for CAs of this kind, which goes like this. That means it has 4 states. It's a, oh, sorry. 4, no, 5, it's correct. So 4 is the survival. So if it's dead, if it's alive and it has 4 neighbors, that's the survival. 4 is also the dead. So the second part is dead. It is dead. Sorry, I'm confusing. The birth, not the death. So if it's dead and it has 4, then it's alive, so it gets born. That's what the second number means. The 5 is the number of states. In this case, we have 5 states. And M is the neighborhood, the Moore neighborhood. If it's N, then it's von Neumann neighborhood. So this notation you will see around the 3D systems, and that's what it means. Okay. Okay, so let's see if this does something. Maybe not. And then I'm just gonna copy it because maybe I forgot something. I'm not gonna spend time debugging this. We reset, so we reset. Set. No, reset. And see what happens. I don't see anything happening. Should I do something here? That's quite obvious. Oh, of course, I'm not passing the states yet here. So let's see if we see that state. He's complaining. Okay. Already should go to 3. Okay, let's see if something happens. Yes, there's something going on there. Great. But now we need to see this somehow, right? Because we cannot really tell what's going on here. And to do that, we're going to use the visualizer that we did already, right? So let's use this visualizer. And we have one problem though. This is 8-bit. I forgot to make it 32-bit because remember that we have values that are higher than 1. We can have up to number 4. So let's do it 32-bit and do it again. Yeah. Now it's not staying alive, but still doing something. Yeah, okay, that doesn't matter. We're gonna use the visualizer to see what's going on. If you see when I reset, it gives me a little ball there. Okay, so I probably forgot something here in the code. I'm just gonna quickly copy it so I don't waste time doing that. And that should give me something that works, I hope. Otherwise, I just copy the one here. That is better. Let me just copy this. Didn't waste time. Okay. Okay, so we do this. That will be rule 445 when you do it correctly, of course. We will show you that that's indeed the check neighbors. That is rule 445, the one we just implemented here. I will do 405. I'm reusing the visualizer from the 2D stacks, and now you get this result, as you can see here. Yeah. Okay, so this should be 5. Okay. You can come up with different rules, but the key element, key takeaway for this is that you can generalize that to that form: the earth rule, survival rule, and decay rule. So as you can see, all of them have a survival, a birth, and decay. Yeah, all of them have the same structure, and the only thing that changes really is the checks here. Which ones to check to see if it's alive, which ones to check if it's dead, and the number of states. So we can generalize this, since the algorithm is regular, so we can generalize this into a better form, and we don't have to write all the time these rules. So let's do that. I'm going to now show you how I generalize it, and then we are done. So let's see, 3D systems. The way to generalize it, one possible way is to do it like this. So you have, I added here some parameters to create a survival rule and a birth rule, as you can see here. And I make a shader dynamically using those and creating code. Similar to what I did with the Slacker set, this is done with a class. You can read it to see how I did it. It's quite simple. It's just this. This is just creating shader code based on those parameters. And then we can easily and dynamically control this. So we can create some rules. For example, this one doesn't seem to do much right now. Maybe with a better probability or a different radius. Yeah, radius. This seems to work. So as you see, they are kind of sensitive to small conditions. So you need to find what works. That takes a little bit of time. But once you find something, there you go. Okay. You can choose also, I added what to do on the edges like we did before. If you wrap it to climb to 0, you can change the number of possible states all dynamically. So while it's running, you can update this and see what happens. And you can update the rules. And some of these rules that I include here, the author was Jason Rankoff. He has a great blog called Septology. I'm going to give you a link also to that. I recommend you to check that out. It's pretty cool. It's a great resource. But still, I was not satisfied with this for the workshop. So for this workshop, I really wanted to give you something that you can plug and play and just have fun. Don't have to type code anymore. So I created this. And this is the general purpose 3D system. And what you can do here, I give you a nice interface. And you can basically play here. For the survival, you can choose all the values that you need or you want for them to survive here using this interface. So let's start from 0. Maybe I want that only if there's 4 neighbors, it survives. And if there's 4 neighbors, it is born, then that works. I also provide some presets here that you can try. The 3D brain, 445 amoeba. So you try one of these, then then you can see how it looks like. Let's try. It's one of my favorites. It's one of the promo video builder. These ones I took from Jason from his rule sets. So you can explore all these. Some of them are pretty interesting stuff. But you can also, like I said, create them using this tool here. So just select the ones you want to be for each rule and then try. Sometimes you get really interesting things. Sometimes you get most of this. Of course, you can update the number of states. You can change the neighborhoods from Neumann mode, and you can play around in this way. And it will allow you to dynamically explore. Okay, so I provide this tool. I hope you have fun with it. I don't have time to explore more. I want to explain more about rendering, making it look pretty. We skip all that so that you know everything there is to know, at least to some level about this. You can dive into the code. As I said, for the 1D versions, there's video and the game of life actually as well. I made already videos, tutorial videos that are free on my YouTube channel. You can check those. And for the MNCAs on this. I provided tools that I hope work for you and that you can learn from that and enjoy it. Yeah. So I think that's all for today, unless there are some pressing questions. I don't know if there's space for questions. Let me know.
Thank you, Darren. So yeah, so if anyone have question, please feel free to post your question on the chat.
Yeah, you can post it there. I'm happy to answer questions. Oh, yeah.
There is a few time lag for the YouTube. So.
Yeah. Yeah, okay. I don't think there's questions, so either it's all clear or you want to explore them yourself, that's all fine. Oh yeah, thanks so much for you to join, and thanks a lot for TDSW for the invitation.
You're very welcome.
It was quite compressed, but I hope there's enough there to dive deep. And I was very happy to prepare this.
Darren, do you have anything to share? For example, your work or exhibition or anything you have?
What should I share?
If nothing, it's okay. Just just pop up.
Yeah, I think it's all good. I think if I want to share something, it would be more links to what I explained. Unfortunately, I didn't have much time to put the links before the workshop. I will do this for the later on for you to join for Patreon. But you can find a lot of information online. One thing I recommend to check is definitely the interviews with Wolfram. This is, for example, a nice interview that you can find about Rule 30. Why it's so interesting? I mean, the subject of cellular automata is very, very fascinating. So there's so many things you can learn about it. Just dive in, read about the philosophy. I didn't give you anything about the philosophical view of it, the implications for computation behind it. But check, for example, things like this interview with Wolfram about Rule 30, or read about his blog. For example, you can read about Totallistic cellular automata in this, which I provide as well in one of the links in the code. So all the code has some links from where I took ideas and where I learned some rules. And yeah, please go ahead and read those to have a better understanding. And I want to leave you as well with this one from Stephen Wolfram as well. He has developed some theory of physics based on cellular automata. This was quite the news a couple of years ago. Many skepticism, but it's still fascinating to read what his way of thinking is regarding the implications of automata for our reality and what that could work. So yeah, thank you again. I hope this gives you enough information today.